Imagine for a second that you are standing next to a rocket about to fly to Mars. It is fully fueled. The tanks are packed. Enormous cylinders of liquid oxygen and kerosene, white with frost, tower above you for dozens of feet. And here is the thing. Almost everything you are looking at is fuel. 90% of this rocket's mass is not the hull, not the instruments, not the crew capsule. It is propellant. Propellant needed to accelerate the propellant, which is needed to accelerate more propellant, which is needed to deliver a few tons of useful cargo to Mars. It sounds insane, but that is exactly how every rocket ever built by humans works. We burn mountains of fuel for a tiny sliver of payload at the very top. And the reason comes down to a single equation, written in 1903 by a nearly deaf schoolteacher in a provincial Russian town called Kaluga. An equation that governs everything we do in space. An equation you cannot escape. Or almost cannot. Because in the middle of the 20th century, a group of engineers in the Nevada desert tried to cheat that equation. They built a rocket engine in which nothing burned. Nothing at all. Instead of a chemical reaction, there was a white-hot nuclear reactor. Instead of combustion products, there was pure hydrogen, heated to unimaginable temperatures and blasted out through a nozzle. And you know what? It worked. The engine passed every test. It restarted 28 times inside a vacuum chamber. It was ready to fly. And then it was killed. Not because it broke, not because the physics failed, but because a new president moved into the White House, and on the other side of the world, a war was eating the budget alive. And this is where it is worth stopping and asking a few questions that, I think, hit closer to home than you might expect. Why does it cost $1 billion to send anything beyond Earth's orbit? Why is a trip to Mars still 9 months trapped inside a metal tube, soaking up cosmic radiation with every passing week? Is there a hard wall in physics, a ceiling that chemical rockets simply cannot punch through, no matter how good the engineering gets? And if someone already found a way past that wall 50 years ago, tested it, proved it worked, and wrote down everything they learned, why are we still stuck on this side of it? To answer all of these, we need to start at the very foundation, with how a rocket actually moves, with the equation that sets the rules, and with the reason those rules are so brutal. Let us figure out how a rocket works. For real, not at the level of fire shoots out the bottom and the thing goes up, but at the level where the rest of this story actually makes sense. A rocket is the only vehicle that works in a vacuum. An airplane pushes against air. A ship pushes against water. A car pushes against the road. Tires gripping asphalt. Friction driving the whole thing forward. A rocket in space has none of that. No medium, no surface, nothing to push off of. All it has is Newtonian mechanics in their purest form. The third law. Every action produces an equal and opposite reaction. The rocket throws mass one way and moves the other way. That is it. The entire principle of rocket propulsion fits in one sentence. Throw something backward fast enough and you go forward. Beautiful, simple, elegant, and absolutely ruthless once you start doing the math. Because here is what the arithmetic looks like. To accelerate, the rocket needs to throw mass overboard. That mass is fuel. But fuel is also cargo that needs to be accelerated along with the rocket before it can be thrown out. You load a ton of fuel, and now you need to accelerate not just the payload, but also that ton. And to accelerate the extra ton, you need more fuel, which also needs to be accelerated, which demands more fuel. A closed loop, and it is not linear. it is exponential. Every additional foot per second of speed costs not a little more fuel, but disproportionately, catastrophically more. This is exactly what Konstantin Tsiolkovsky described in his 1903 paper, Exploration of Outer Space by Means of Rocket Devices. Tsiolkovsky is a remarkable figure. Nearly completely deaf after a childhood bout of scarlet fever, with no formal higher education, he taught physics and mathematics at a provincial school in Kaluga, south of Moscow. And in that schoolroom, in the silence of his own deafness, he derived the equation that would define the entire future of space travel. His formula links three things: the final velocity of the rocket, the exhaust velocity of the gases leaving the nozzle, and the ratio of the rocket's starting mass to its ending mass, meaning how much fuel you burned along the way. And the formula says this: the relationship between the rocket's velocity and the amount of fuel spent is logarithmic. To get a gut feel for what that means, think of it this way. If a regular car burns gas linearly, drive 60 miles, burn 2 gallons, drive 120, burn 4, then a rocket works completely differently. To gain, say, the first mile per second of speed, you might need to burn 60% of the rocket's mass. To gain one more, 60% of what is left. And one more, 60% of the remainder. With every step, you are spending a monstrous fraction of what you have left. And the payload, the part you actually care about, shrinks to a razor-thin sliver at the very top. Let us put real numbers on this, because abstract math is one thing and the gut punch of scale is another. To reach low Earth orbit, you need to hit roughly 5 miles per second, or about 26,000 feet per second. A good chemical engine, say a hydrogen-oxygen engine, the most energetically favorable combination available, pushes exhaust out the nozzle at around 2.5 to 3 miles per second. Plug that into Tsiolkovsky's equation, and the mass ratio comes out to roughly 6 to 1. The rocket at launch weighs 6 times more than after all the fuel is burned. 5/6 of the starting mass is propellant. 1/6 is structure, engines, instruments, and somewhere in the remaining fraction, the actual payload. The Saturn V, the rocket that carried astronauts to the moon, weighed about 6.5 million pounds at launch. It delivered roughly 100,000 pounds to lunar orbit, about 1.5% of its starting weight. Everything else was fuel and empty tanks dropped along the way. And here is the critical thing to understand. This is not a failure of engineering. Engineers have spent 70 years pushing chemical rockets to within a hair of the theoretical limit. SpaceX's Raptor engines, the RS-25 from the Space Shuttle, the Vulcain from Europe's Ariane, they all operate at staggering thermodynamic efficiency. Combustion chambers withstand temperatures that melt most metals. Turbopumps spin at tens of thousands of revolutions per minute, shoving hundreds of gallons of fuel through every second. The engineering is at the edge. The problem is the chemistry itself. The fundamental ceiling on the energy locked inside chemical bonds. When you burn hydrogen in oxygen, the most energetic chemical pair you can find, you get water. H2 plus O2 gives you H2O plus energy. And the speed at which that superheated steam blasts out the nozzle is limited by how much energy gets released when some bonds break and new ones form. Chemical bonds hold a fixed amount of energy per unit mass, and you cannot squeeze more out of them. No engineering trick will change that. It is a ceiling built into the structure of atoms and molecules. A glass ceiling that we have been pressing our heads against for decades. For getting to orbit and back, that ceiling is good enough. We have learned to live with it. We build multi-stage rockets, where each stage drops away after burnout, so you do not have to haul empty tanks any further. a trick that Tsiolkovsky himself proposed. We use gravity assists. A spacecraft swings past a planet, hooks onto its gravity, and the planet, like a giant sling, hurls it faster, for free, without burning a single drop of fuel. In 1965, a Caltech graduate student named Gary Flandreau noticed that in the late 70s, the giant planets would line up so that a single spacecraft could fly past Jupiter, Saturn, Uranus, and Neptune, gaining speed at each flyby. That alignment happens once every 175 years. The Voyagers used it, and Voyager 1 is now about 15 billion miles from Earth, beyond the reach of the solar wind, in interstellar space. Nearly 50 years in transit. All of these are ways to live inside Tsiolkovsky's equation without trying to cheat it. Staging, gravity assists, reusable first stages, all of them work with the exhaust velocity that chemistry gives you. And for robots, probes, and satellites, that is plenty. A probe does not care how long the trip takes. 35 years? Fine. It has no bones to lose calcium, no cells damaged by radiation, no mind cracking under confinement. Humans are a different story. Humans need to get there fast, and fast, on an interplanetary scale, is a completely different problem from fast in low Earth orbit. For orbit, you need about 5 miles per second. For a trip to Mars on the most fuel-efficient trajectory, you need roughly 2.5 miles per second to break away from Earth, and about 1.25 to slow down and be captured by Mars. Round trip, fully propulsive, the total change in velocity, what engineers call delta V, adds up to roughly 7.5 miles per second. That is, if you take the cheapest route, a Hohmann transfer, 9 months each way, with launch windows that open once every 26 months. Want to go faster? You need more delta V. 5 months? Add more. 4? Even more. And every additional 1/10 of a mile per second costs exponentially more fuel. You cannot negotiate with Tsiolkovsky. And here is the trap. The real trap that turns every conversation about crewed Mars missions into a brick wall. You want to fly faster, so you take more fuel. But more fuel means a heavier rocket. A heavier rocket means even more fuel to push it, and more, and more. The exponential works against you. But wait. You do not just need to speed up. You also need to slow down. Space has no brakes, no atmosphere thick enough to stop a heavy crewed ship at Mars. To stop, you have to flip the ship around and fire the engine the other way, burning roughly as much fuel as you use to speed up. The exponential bites you twice, once on departure and once on arrival. You could take more cargo, more food, water, equipment, radiation shielding to keep the crew alive for 9 months. But every extra pound of payload demands several more pounds of fuel by Tsiolkovsky's equation. You fight the math, and the math wins. An engineer designing a Mars mission on chemical rockets makes agonizing trade-offs every single day. Faster or more cargo? Radiation shielding or food supply? Bigger engines or lighter structure? Every choice is a sacrifice, and the root of all these sacrifices is one number: specific impulse. Specific impulse. Let us park here for a moment, because this concept is going to be the key to everything that follows. Specific impulse is a measure of how efficiently a rocket engine uses its fuel. It is measured in seconds, which sounds odd, but there is a clean idea behind it. Take 1 pound of propellant. Make the engine produce 1 pound of thrust. Specific impulse is the number of seconds that pound of fuel can sustain that thrust. More seconds means the engine wrings more work out of every ounce of propellant. You can look at it another way, through the formula. Specific impulse is directly tied to exhaust velocity. It is basically exhaust velocity divided by the acceleration of gravity. The mass flow rates in the numerator and denominator cancel out, and all you are left with is how fast the exhaust is moving. That is it. Want higher specific impulse? Make the exhaust go faster. The best chemical rockets top out at about 400 to 460 seconds. The Merlin engine on a Falcon 9 does around 320 at sea level, 340 in vacuum. Raptor hits roughly 350 at sea level, about 380 in vacuum. Hydrogen-oxygen engines like the RS-25 from the shuttle reach 453 seconds, among the best in history. And beyond that, chemistry says no. The bond energies of HH and OO set the ceiling, and we are pressed flat against it. The entire story I am about to tell starts with one simple question. What if you could change the number in the denominator? What if you could make the exhaust fly out of the nozzle twice as fast? Tsiolkovsky's equation is not going anywhere. It is fundamental, as unbreakable as conservation of momentum. But if you raise the exhaust velocity, the entire exponential curve shifts in your favor. You need exponentially less fuel for the same maneuver. Or, with the same fuel load, you can pull off an exponentially bigger one. Fly faster, go farther, carry more. Doubling specific impulse, going from 450 seconds to 850, is not twice as good in a straight line sense. In the world of exponentials, it is a radical, qualitative shift in the entire mission. A Mars trip shrinks from 9 months to 4 or 5. Or you fly the same 9 months, but bring twice the payload. Or you launch not just inside the narrow optimal window, but across a much wider range of dates, because you have enough delta V margin to take less efficient trajectories that a chemical rocket could never afford. For an engineer building a Mars mission, an engine with 850 seconds of specific impulse feels like someone just doubled the budget. Every constraint loosens. Every either-or turns into both. Speed and cargo. Radiation shielding and food. Orbit capture and fast transit. The only question is, where do you get 850 seconds? What energy source can push gas out of a nozzle twice as fast as the hottest chemical reaction? The answer turned out to be disarmingly simple. So simple that when you first hear it, it sounds like someone is joking. But before we get there, let us put concrete numbers on the trap, because feeling the scale matters more than understanding it in the abstract. Take a specific mission. Say we want to send a crewed habitat module weighing about 110,000 pounds to Mars and bring the crew back. Life support, food, water, science gear, a lander for the surface. 110,000 pounds is roughly the mass of the International Space Station without its solar arrays and truss. Sounds like a lot, but for a 3-year mission, it is closer to the bare minimum. How much fuel does a chemical rocket need? We will use a hydrogen-oxygen engine at 450 seconds, the best available. The delta V budget for a fully propulsive round trip, Earth to Mars and back, on home and transfers with orbit captures, adds up to about 7.5 miles per second. Plug that into Tsiolkovsky at an exhaust velocity of about 2 3/4 miles per second. The mass ratio is e to the power of 7.5 divided by 2.75, which comes out to roughly 15 to 1. To deliver 110,000 pounds of useful mass and return the crew, the ship needs to weigh about 1.7 million pounds at departure from Earth orbit. About 1.6 million pounds of that is fuel, 1.7 million pounds in orbit. A Saturn V could put about 286,000 pounds into low Earth orbit. You would need 6 Saturn V launches, or their equivalent, just to assemble one Mars ship. At billions of dollars per launch, the fuel delivery alone runs into the tens of billions. And that is before you count the ship itself, mission control, or crew training. Now the same calculation with a nuclear thermal engine. Specific impulse, 850 seconds. Exhaust velocity, roughly 5.2 miles per second. Same delta V of 7.5 miles per second. The mass ratio drops to e to the power of 7.5 divided by 5.2, which is about 4.2. Starting mass, roughly 460,000 pounds. Fuel, about 350,000 pounds of hydrogen. 460,000 pounds instead of 1.7 million. Nearly 4 times less. 2 heavy lift launches instead of 6. The difference is not incremental. It is the difference between a program that might actually get funded and one that stays on paper forever. There is a nuance. Liquid hydrogen is about 14 times less dense than a kerosene-oxygen mix, so the tanks for 350,000 pounds of hydrogen would be enormous.
Tank structure adds weight. Insulation adds more. The real numbers come out somewhat worse than the raw Tsiolkovsky calculation. But even accounting for all engineering realities, the advantage is measured in multiples, not percentages. This is why the engineers of the 1960s did not treat nuclear propulsion as an option or one of many research directions. For them, it was the only realistic path to crewed Mars. Without it, a Mars mission was technically possible, but logistically crushing. 6 heavy launches for one expedition is not an engineering project, it is a fantasy. 2 launches is a project. The line between can do but insanely expensive and hard but real runs right along the specific impulse axis. 450 seconds on one side, 850 on the other. Here is the idea. What if you did not burn anything at all? Let us look one more time at how a conventional chemical rocket engine works and find the weak link in the chain.
A chemical engine takes 2 ingredients, fuel and oxidizer, say hydrogen and oxygen. Turbopumps force both into a combustion chamber under tremendous pressure. Inside the chamber, they mix and ignite. An exothermic chemical reaction follows. Hydrogen atoms bond with oxygen atoms, forming water. Energy is released, the energy that was stored in the original chemical bonds. That energy heats the reaction products, superheated steam, to thousands of degrees. The hot gas expands, rushes toward the only exit, a specially shaped nozzle called a de Laval nozzle, and blasts out the back at enormous speed. The nozzle's contour accelerates the flow even further, converting thermal energy into directed motion. Gas goes backward, rocket goes forward. Newton's third law. Now notice something. In this setup, the energy source and the working fluid are the same thing. The fuel is simultaneously what provides the energy through the chemical reaction and what flies out the nozzle as exhaust.
You cannot separate the two. And because of that, you are stuck with whatever molecules the reaction produces. Burn hydrogen in oxygen, you get water, molecular weight 18. Burn kerosene, You get a mix of carbon dioxide and water, even heavier. You are a hostage to chemistry. Whatever the reaction gives you, that is what comes out. Now imagine splitting those two jobs apart. Energy source, separate. Working fluid, separate. The energy comes from somewhere else, and you pick the working fluid yourself, the lightest, the most convenient, the best for generating thrust. No combustion, no chemical reaction. You just take a gas and heat it with something extremely hot. The gas expands, flies out the nozzle, and you have a rocket engine. What could that something extremely hot be? What energy source can heat a gas hotter than any chemical reaction while being compact enough to fit inside a rocket? A nuclear reactor. That is the entire principle of a nuclear thermal rocket, or NTR.
And if you step back and look at it from a distance, it is strikingly similar to a device humanity invented 300 years ago. Thomas Newcomen's steam engine, built in 1712, worked like this. You burned coal, heated water. The water turned to steam. The steam expanded and pushed a piston. Energy source, burning coal. Working fluid, water. Useful work, the expansion of steam. A nuclear thermal rocket engine works on the same principle. Energy source, nuclear fission. Working fluid, hydrogen. Useful work, blasting superheated gas out the back. Instead of a cast iron cylinder with a piston, you have a de Laval nozzle. Instead of coal, you have uranium-235. Same idea. Heat a working fluid, extract work from its expansion. 3 centuries, and the core concept has not changed. Now let us break down how the engine is physically built, because its simplicity at the concept level is both its greatest strength and the doorway to every engineering nightmare that follows.
At the heart of the engine sits the core of a nuclear reactor.
Picture a compact cylinder packed with fuel elements made of enriched uranium-235. These elements can take different shapes, rods, hexagonal blocks, plates, but they all share one feature. They are riddled with thin channels. Dozens of channels running through the body of each element, like capillaries through a sponge. Those channels are where the working fluid, hydrogen, will flow. Uranium-235 sustains a fission chain reaction. A neutron strikes a uranium-235 nucleus. The nucleus splits into 2 fragments, releasing enormous energy, roughly 200 million electron volts per fission, tens of millions of times more than a single chemical reaction. And critically, 2 or 3 new neutrons fly out, each capable of splitting another nucleus. A chain reaction, a self-sustaining process that generates heat, a tremendous amount of heat.
The core temperature of a nuclear rocket engine can reach about 4,500 degrees Fahrenheit.
For comparison, the standard power-generating nuclear reactors on Earth, the ones that boil water to spin turbines at power plants, run at around 570 degrees Fahrenheit. They do not need more. Their job is to make steam, and water boils at 212 degrees, higher under pressure, but still far from thousands. A rocket reactor needs to heat hydrogen to the highest possible temperature, because the hotter the gas, the faster it leaves the nozzle. So the rocket reactor runs an order of magnitude hotter than its power plant cousin. 4,500 degrees Fahrenheit is a temperature at which most metals have long since melted. It is closer to the surface temperature of certain stars than to anything in daily life. Now, through those channels in those white-hot fuel elements, a turbopump forces liquid hydrogen.
The hydrogen enters the reactor from the tank as a cryogenic liquid at about -423 degrees Fahrenheit, 36 degrees above absolute zero. The temperature gap between inlet and outlet is nearly 5,000 Fahrenheit, and the hydrogen crosses that gap in a fraction of a second, racing through the narrow channels of the core. Liquid becomes gas instantly. The gas heats to thousands of degrees. Hydrogen molecules, loaded with kinetic energy, rush toward the only exit, the rocket nozzle, and blast out at tremendous speed. No combustion, no chemical reaction. Hydrogen goes in as hydrogen and comes out as hydrogen. Just very, very hot hydrogen. If you could collect that exhaust and cool it back down, you would get exactly the same hydrogen you loaded into the tank. Nothing changed chemically. Only the temperature changed, and therefore the speed of the molecules. Hotter gas, faster molecules, higher exhaust velocity, higher specific impulse. That is the entire logic. That is the whole engine, reactor, channels, turbopump, nozzle. In terms of moving parts, it is radically simpler than a chemical rocket engine. A liquid fuel rocket engine requires injection of two propellants through hundreds of injector orifices, precise mixing, ignition, stable combustion. Fighting acoustic oscillations inside the combustion chamber is one of the hardest problems in rocket engineering, and active cooling of chamber walls that sit in direct contact with gas at over 6,000 degrees Fahrenheit. A nuclear thermal engine has none of that. No two-component system, just one fluid, hydrogen. No combustion, so no combustion stability problem. No oxidizer, so no risk of a detonation from premature mixing. The moving parts, literally, fall into two categories. The turbopump, which pushes hydrogen through the reactor, and the control elements, rotating drums positioned around the perimeter of the core. Each drum is coated with a neutron reflector on one side and a neutron absorber on the other. When the reflective side faces the core, neutrons bounce back in, sustaining and strengthening the chain reaction. Temperature climbs, power rises. When the absorbing side rotates inward, neutrons get soaked up, the chain reaction weakens, power drops. That is your throttle and your brake. Smooth rotation of the drums lets you precisely control reactor power and, therefore, hydrogen temperature and engine thrust. Now, why does all of this produce such a massive advantage in specific impulse? Let us walk through the physics step by step, because this is where the key to the entire story is hidden. In any thermal rocket engine, chemical or nuclear, the exhaust velocity is determined by two things: the temperature of the gas and the molecular weight of the particles you are throwing out the back. This follows from basic thermodynamics. Thermal energy converts into kinetic energy of directed molecular motion. Kinetic energy is 1/2 mass times velocity squared. If we want velocity, we flip the formula. Velocity equals the square root of 2 times energy divided by mass. The more energy you pump into a molecule, the faster it flies. And the lighter the molecule, the faster it flies for the same energy input. Both factors work in favor of the nuclear thermal engine. First factor, temperature. A nuclear reactor can heat gas to temperatures comparable to chemical combustion, or even higher. 4,500 degrees Fahrenheit in a nuclear engine is less than the 6,000 plus in the combustion chamber of an RS-25, but it is in the same ballpark. The energy deposited per molecule is roughly comparable. Second factor, and this is the decisive one, the molecular weight of the working fluid. When you burn hydrogen in oxygen, the exhaust is water.
Molecular weight of water, 18.
When you run pure hydrogen through a nuclear reactor, the exhaust is hydrogen. Molecular weight of molecular hydrogen, H2, 2. 9 times lighter. Exhaust velocity scales inversely with the square root of molecular weight. Square root of 9 is 3. At the same temperature, pure hydrogen exits the nozzle 3 times faster than steam. In practice, the temperatures are not identical and there are various losses, but the bottom line is that a nuclear thermal engine comfortably reaches 800 to 900 seconds of specific impulse. Twice the best chemical engines. Twice. Remember that number, because in the world of Tsiolkovsky's equation, twice is not slightly better. It is a revolution. Plug 850 seconds instead of 450 into a Mars mission mass budget, and the picture shifts tectonically. Same starting mass, but now you can fly to Mars in 4 to 5 months instead of 9.
Or you fly the same 9 months, but carry twice the payload. More food, more water, more radiation shielding, more science gear, more spare parts for life support. Or, and this is just as critical, you launch not only inside the narrow optimal window every 26 months, but across a much wider range of dates, because the delta V margin lets you take less efficient trajectories that a chemical rocket simply could not handle. It sounds like a dream. And at the level of the principle, it really is that simple. Put in a reactor, run hydrogen through it, get an engine twice as good. But between the principle and a working engine lies a chasm filled with hundreds of engineering problems. And the most fundamental one, the one that threads through the entire history of nuclear propulsion, is tied to the very hydrogen that makes this engine so brilliant.
Because hydrogen is, without exaggeration, the most temperamental, most inconvenient, most infuriating substance that rocket engineers have ever had to work with. There is something else worth saying about why this seemingly obvious idea, just heat gas and push it out, took so long to turn into hardware. The gap between a ground-based nuclear reactor and a rocket reactor is enormous. A commercial power reactor runs at about 570 degrees Fahrenheit, comfortable for making steam. The structure is steel, layered with multiple safety barriers, cooling systems, massive margins everywhere. Everything is robust, proven, refined over decades of operation. A rocket reactor runs at 4,500 degrees, an order of magnitude hotter. At those temperatures, steel is a puddle. You need different materials entirely: graphite, carbides, nitrides, refractory metals. The fuel elements are not standard rods of uranium oxide in zirconium cladding, like at a power plant. They're custom-engineered composites. Uranium-235 dispersed in a graphite matrix, coated with thin layers of niobium carbide, or zirconium carbide, to resist both the temperature and the chemical attack of hot hydrogen. Building those fuel elements was an engineering saga in itself. Each element is a compromise. It has to transfer heat to hydrogen efficiently, meaning lots of surface area, lots of fine channels, while remaining strong enough to withstand thermal stress and gas pressure, and while resisting chemical erosion by hydrogen for the full duration of the engine burn. Those three requirements partly contradict each other. More channels mean thinner walls, mean less strength. Higher temperatures mean better performance, but also more erosion. The NERVA program, which we will get to,
iterated through hundreds of fuel element designs. Every reactor test was a lesson. Where did the coating crack? Where did hydrogen find a weak spot? Where did the thermal shock fracture the graphite? Each post-test teardown of an irradiated reactor, done remotely with robotic arms behind thick leaded glass, generated data that is essentially irreplaceable today. Because to reproduce those results, you would need to build a reactor, heat it to 4,500 degrees, run hydrogen through it, and then disassemble it to see what survived. The cost of a single such cycle today would be tens of millions of dollars. NERVA ran more than 20. And there is one more comparison worth making. A liquid fuel chemical rocket engine is one of the most complex devices ever built by humans.
The combustion chamber, the injector plate with hundreds of precisely machined holes, the regenerative cooling system where fuel flows through channels in the chamber walls to keep them from melting, the turbopumps for two separate propellants, the gas generators or pre-burners to drive the turbines, the valves, regulators, ignition systems. The RS-25 had roughly 50,000 individual components. A nuclear thermal engine uses one propellant instead of two, no combustion chamber, just channels in the core. No injector plate, just an inlet manifold. No ignition system, nothing to ignite. Not two turbopumps, one. No mixing problem, nothing to mix. Structurally, it is radically simpler. That does not mean it is easy to build. The reactor brings its own set of challenges: neutronics, radiation resistance, thermal stress. But in terms of moving parts, in terms of potential failure points, a nuclear thermal engine is simpler than a chemical one.
And the NERVA engineers saw this in practice. Even when Kiwi B reactors shook themselves apart, the engines kept running. When NRX was asked for 28 restarts, it delivered all 28. This was a program that by and large did what it was asked to do, on time and on budget, which, in the space industry, deserves a monument of its own. So, hydrogen. Element number 1 on the periodic table, the lightest atom in the universe, the smallest molecule, and the only working fluid that makes a nuclear thermal engine worth building. Why hydrogen, we have already covered. Exhaust velocity scales inversely with the square root of molecular weight, and hydrogen has the lowest molecular weight of any substance that exists. Molecular hydrogen, H2, has a weight of 2. Nothing lighter is possible. But let us run a thought experiment that will make it absolutely clear why a nuclear thermal engine has no choice. Hydrogen or nothing. Suppose you decided to swap hydrogen for something easier to handle. First candidate, helium. Inert, safe, does not react with anything. Atomic weight, 4, twice as heavy as hydrogen. Plug into the formula. Exhaust velocity drops by the square root of the mass ratio, meaning the square root of 2, roughly 1.4 times. Specific impulse falls from 850 seconds to around 600. Still better than chemical, but the advantage is fading. And helium is rare, expensive, and also leaks through tank walls because its atoms are only slightly bigger than hydrogen's. Questionable trade. Fine, let us try something heavier but genuinely convenient. Nitrogen. 78% of Earth's atmosphere, available in unlimited quantities, stores at reasonable temperatures, inert under most conditions. Molecular weight of N2, 28, 14 times heavier than hydrogen. Exhaust velocity drops by the square root of 14, which is 3.7 times.
Specific impulse lands at about 230 seconds. 230. Reminder, a good chemical engine on hydrogen and oxygen gives 450. So a nuclear engine running on nitrogen performs half as well as a regular chemical rocket. You are dragging around a heavy, dangerous, radioactive nuclear reactor and getting worse performance than if you had just burned kerosene. Complete absurdity. Go further down the periodic table. Ammonia, molecular weight 17. Specific impulse drops. Methane, 16. Also worse. Carbon dioxide, 44. Hopeless. Xenon, used in ion engines, 131. Not even worth discussing. That is the entire thought experiment. One step to the right of hydrogen on the periodic table, and a nuclear thermal engine loses its reason to exist. No alternatives, no workarounds. Hydrogen is the only element that makes NTR worthwhile. And that means every single problem hydrogen has is automatically your problem, forever.
And hydrogen has quite the catalogue of problems. Problem 1. Density. Liquid hydrogen is the lightest of all liquids. Its density is about 4.5 pounds per cubic foot. For comparison, water is over 62 pounds per cubic foot. Kerosene is about 50. Liquid oxygen is 71. Liquid hydrogen is 14 times less dense than water. What does that mean in practice? It means your fuel tanks have to be enormous, colossal. Picture a Mars ship, a small crew module at one end, a nuclear reactor at the other, and between them, gigantic cylindrical tanks occupying most of the vehicle's length. And inside those impressive-looking tanks, by weight, there is not that much hydrogen. You are hauling mostly tank structure, walls, insulation, frames, stiffeners, and the hydrogen inside by mass is modest. All that structure is weight, and weight needs fuel to accelerate. Tsiolkovsky grins. You try to cheat his equation with specific impulse, and he hits you back with tank mass.
Problem 2. Cryogenics. Liquid hydrogen exists only below -423 degrees Fahrenheit, 36 degrees above absolute zero, one of the lowest boiling points of any substance. Maintaining that temperature is an engineering discipline in itself. On Earth, while a rocket sits on the launch pad, hydrogen boils off constantly. Crews literally top off the tanks until the last seconds before liftoff. The tank steams, white clouds cascading down the hull. That is not engine smoke, that is hydrogen boiling off and hitting moist air. In space, there is no top-off. Hydrogen warms up. Sunlight, infrared radiation from Earth, heat from onboard systems, everything adds energy. Molecules gain kinetic energy, the liquid starts to boil. Gaseous hydrogen builds pressure inside the tank. If you do not vent it, the tank bursts. So you open a relief valve and let hydrogen escape into space. Every gram vented is lost propellant.
This process is called boil-off, and it never stops. Every hour you wait in orbit is lost fuel. For a Mars mission, this is a critical problem. Picture a scenario. The ship is assembled in low Earth orbit. Cargo flights deliver components, fuel, supplies. Assembly takes weeks, maybe months. Then you wait for the launch window, the right alignment of Earth and Mars. The whole time, hydrogen is boiling away. You fueled the ship, but while you were assembling and waiting, some of the fuel evaporated. You either need to refuel, which means additional expensive launches, or solve the storage problem from the ground up. Engineers are working on it. Multi-layer vacuum insulation, sun shields, active cryo-coolers that remove heat and radiate it away. Zero boil-off remains an engineering goal that people are approaching but have not yet reached. Problem 3. Leakage. This is perhaps the most counterintuitive and most maddening aspect of working with hydrogen.
The hydrogen molecule, H2, is so small that it can permeate through the crystal lattice of metals, literally pass between the atoms of the tank wall, like sand through a coarse mesh. Hydrogen is the smallest atom in the universe, and its diatomic molecule is the smallest of all molecules. You can weld a perfect seam, polish the walls to a mirror finish, use the densest alloys available, and hydrogen will still slowly, relentlessly seep through. In the vacuum of space, where the pressure difference between inside and outside the tank is at maximum, diffusion accelerates. Hydrogen wants out. It is actively, persistently trying to escape any container you put it in. Every engineer who has worked with hydrogen describes it with the tone of someone talking about a particularly difficult pet. Hydrogen runs. Hydrogen leaks. Hydrogen pretends it is not there and then shows up where you least expect it. Storing hydrogen means waging a continuous war against the smallest fugitive in nature.
Problem 4. Specific to nuclear engines. Hydrogen's aggressiveness at high temperatures. When hydrogen heats to thousands of degrees, it becomes chemically very reactive. It attacks the materials of the reactor core, penetrates the structure of fuel elements, causes hydrogen embrittlement, reacts with carbon in the protective coatings, eats away at barrier layers. The fuel elements of a nuclear rocket engine operate at temperatures that would be lethal to most known materials. And on top of that, they are bathed in a stream of aggressive, superheated hydrogen. Engineers coat them with niobium carbide, zirconium carbide, compounds that can withstand both the temperature and the chemical assault. And even with those coatings, erosion happens. Every burn cycle means lost particles of the core. Microscopic fragments of coating and fuel get swept away by the hydrogen stream and exit through the nozzle. The reactor slowly eats itself from the inside out, devoured by its own working fluid.
So there you have hydrogen, savior, because without it, there is no engine. Tormentor, because every single property it has, aside from being light, works against you. Low density, cryogenics, leakage, chemical aggression. 4 problems, each requiring its own engineering discipline. And you cannot walk away from any of them, because there is no alternative to hydrogen. This is exactly the bouquet of challenges that the people who decided, in the mid-1950s, to build the first nuclear rocket engine had to face. They knew the physics. They understood the payoff. They could see that doubling specific impulse was the key to everything beyond the moon. And they knew that hydrogen was the only way to get there, with all its tantrums.
In 1955, a group of physicists and engineers at Los Alamos National Laboratory received funding, $100 million over 3 years, which is over $1 billion in today's money, and an assignment: build and test a nuclear thermal rocket engine. The test site they chose was Area 25 on the Nevada test site, a stretch of desert that had already seen dozens of above-ground nuclear detonations and that locals called Jackass Flats. They were going to tame hydrogen, or at least learn to coexist with it. In the mid-50s, before Sputnik turned the world upside down and kicked off the space race, interest in nuclear propulsion already existed, but not for space, for the military. The Air Force wanted nuclear-powered cruise missiles and strategic bombers capable of circling the globe for weeks without refueling. The reasoning seemed obvious. If a reactor could drive a submarine underwater for months, why not a rocket? In 1953, physicist Robert Bussard published a study on nuclear rocket design. Bussard is a figure worth a story of his own. He would later propose the concept of an interstellar ramjet that scoops up hydrogen directly from the space between stars. But in 1953, his interest was more practical. Could a nuclear rocket engine be built with existing technology? The study caught military attention. A committee was formed, and by 1955 it had issued a recommendation. The best use of this technology was as an upper stage for an intercontinental ballistic missile. Sputnik was still 2 years away. The first real ICBM, also 2 years out. The military was still working with underpowered rockets descended from Germany's V2. Nuclear warheads of that era weighed tons, nothing like the compact thermonuclear weapons that came later.
The idea of strapping a super-efficient nuclear upper stage onto a missile to hurl a heavy warhead across the planet seemed entirely pragmatic. That was how Project Rover was born, an Air Force program handed to the Los Alamos physicists, the same people who built the atomic bomb. Test site, Jackass Flats, Nevada. Territory that had already absorbed so many nuclear blasts that one more source of radiation was unlikely to surprise anyone. And here is where the story goes against expectations. When you hear about nuclear and rocket programs from the 50s, you expect tales of recklessness, accidents, casualties, and a general atmosphere of figure it out as we go. Los Alamos, after all, was the place where classified documents were stored in unlocked cabinets, where critical masses were assembled by hand on a tabletop, where Richard Feynman cracked classified safes for fun. Project Rover was different. They approached the work with a thoroughness that impresses even by today's standards. Years of construction came before the first reactor ever fired. The test complex included liquid hydrogen storage tanks, supply lines, feed systems. Around the test stand, radiation-hardened sensors and monitoring instruments, all rated for the intense neutron and gamma flux from an open nuclear reactor. The control center was a bunker 2 miles away. Over 3.5 miles from the stand, from behind thick walls, operators ran everything remotely. Not a single person was on the test pad during a reactor run. Next to the test stand, they built a specialized building, the RMAD, Reactor Maintenance, Assembly and Disassembly Building. Reactors arrived from Las Vegas in pieces, as kits, and were assembled inside the RMAD. After each test, the irradiated, radioactively contaminated reactor returned to the same building for teardown and analysis. And here is the detail that makes this story unforgettable. To move reactors between the armored and the test stand, the Los Alamos engineers built a small railroad, a real one, with tracks, a locomotive, and a flat car. Except it was operated remotely, by radio. A 25-ton switching locomotive pulled a flat car carrying a nuclear reactor along rails across the desert, while operators in the bunker drove it from 3 miles away. Because after a test the reactor was so hot, radiologically speaking, that no one could go near it. The locomotive was named the Jackass and Western Railway, the world's shortest and slowest railroad. They also had a larger, 55-ton main engine with a center cab and the words Jackass and Western painted on the side. Because apparently everyone on this project had an incurable sense of humor. Picture the scene. Nevada desert, late 1950s. 100-degree heat. A little train crawls along the tracks with a nuclear reactor sitting on an open flat car. 3 miles behind it, inside a concrete bunker, engineers drive it by radio. No one goes near. After testing, the reactor comes back, glowing, radioactive, hot. Men in full protective suits, faces invisible behind glass visors, try to manage the train. There are photographs, and they are glorious. Figures in white suits, clumsy as moonwalkers, standing next to the locomotive. And it is absolutely obvious that they can see almost nothing through those visors. Thank God for the rails. At least the train cannot go off course. Inside the Armad,
irradiated reactors were disassembled remotely using teleoperated mechanical arms. Already in the 50s, they had these arms, large, slow, but functional manipulators that an operator, standing behind thick leaded glass, used to take apart a radioactive assembly piece by piece.
Video footage of these operations survives, and it is mesmerizing. Metal claws gently pulling fuel rods from the core, placing them into containers, unscrewing bolts, lifting housings, all behind glass, all at arm's length. The first reactors intended for testing were never meant to fly. They were research devices, ground only, and so they were named Kiwi, after the flightless New Zealand bird, a small, fuzzy bird that cannot fly. A rocket engine that also cannot fly. Yet, the engineers appreciated the irony. On October 4th, 1957, the world changed. The Soviet Union orbited Sputnik, and panic swept through Western capitals. Eisenhower created NASA to consolidate the competing rocket programs of different military branches, and in October 1958, Project Rover was transferred from the Air Force to the Civilian Space Agency. Fortunately, the transition went smoothly.
Most of the people stayed in place. Work with Los Alamos continued, and the little railroad kept hauling reactors across the desert. The first tests of the Kiwi A series began in July 1959. The procedure was well rehearsed. Reactor assembled in the ARMAD. Loaded onto the flat car. Train carries it to the stand. Flat car locked in place, connected to external liquid hydrogen supply lines. Reactor starts up. External pumps push liquid hydrogen through the core channels. Hydrogen heats, turns to gas, blasts out through the nozzle. The test lasts a few minutes. Instruments on the pad record every parameter: temperature, pressure, flow rate, power. The control bunker observes and commands from 2 miles away. If you find video footage of these tests, and I recommend looking, you will see fire. Bright, orange, impressive fire from the nozzle. Which might confuse you. Did we not just say nothing burns in a nuclear engine? Correct. The hydrogen leaves the nozzle, clean, hot, unburned. The fire comes from a pilot burner installed next to the nozzle. Engineers worried that if hydrogen accumulated in the air above the test pad, it would form an explosive cloud that would eventually detonate. So they ignited it immediately at the exit, turning it into harmless water vapor. The paradox. Fire next to a nuclear reactor for safety. One more important detail. All the hydrogen that passed through a running reactor was contaminated. At those temperatures and neutron fluxes, some fission products, volatile fragments, activated atoms got carried away by the hydrogen stream. The exhaust was radioactive. These early engines were tested in open cycle. Radioactive hydrogen was vented straight into the atmosphere, into the desert air of Nevada. By the standards of the time, this was considered acceptable. The site was on a nuclear test range. Wind usually blew away from populated areas, and concentrations were below the permissible limits of the era, limits that are considerably stricter today. But the fact remains, every Kiwi test was a release of radioactive gas into the open air. The Kiwi A series went reasonably well. Reactors ran, hydrogen heated, thrust was produced. There were minor issues, deviations from predictions, but overall, confirmation, yes, a nuclear thermal engine works in principle. The concept is not just theoretically correct, it functions in practice. Then Los Alamos moved to the Kiwi B series, significantly more powerful and ambitious. And here the real difficulties began. The kind that remind you of the chasm between the principle is proven and the engine is ready to fly. During the test of reactor Kiwi B1B,
the engine began to literally shake itself apart. Vibrations inside the structure built up, and with them, internal components started breaking. Pieces of fuel rods, fragments of cladding, chunks of core structure broke loose and flew out through the nozzle, along with the hydrogen stream. The test pad was scattered with radioactive debris. Not all of it was ever found. Some pieces are still out there, somewhere in the Nevada sand. Engineers did not immediately understand the cause. They moved to the next version, Kiwi B4, described in documents as a radical step forward in complexity and power. Brought it to full power, and again vibrations, again destruction. When the reactor was hauled back to the armored and disassembled with the robotic arms, they found that over 97% of the fuel rods were cracked. 97 out of 100. The cause, when they finally nailed it down, turned out to be tied to hydrogen and its extraordinary properties. Liquid hydrogen, entering the white-hot core, undergoes a lightning-fast phase change from liquid to gas. This transition does not happen gently. The liquid flash boils, its volume expanding hundreds of times in an instant. The result is powerful pressure pulses inside the channels, not an explosion in the usual sense, but a series of extremely rapid expansions that hammer the channel walls, the fuel rods, the entire core structure. The turbo pump forces cryogenic liquid in at enormous speed. The liquid hits the superheated channels, instantly vaporizes, expands violently, and these pressure waves pound every surface inside the reactor, like an invisible jackhammer striking thousands of times per second. 2 years of redesign followed. Engineers had to solve the vibration problem, and they did, by stiffening the structure, modifying channel geometry, adding rigidity. When the improved Kiwis returned to the test stand in 1964, the vibrations were gone. The reactor reached full power, ran for up to 8 minutes, significantly longer than previous models, and, critically, restarted successfully on the same hardware. Reusability. An engine you can only fire once is useless for an interplanetary mission where you need to accelerate, brake, correct course, and maybe come home. Every maneuver means a restart. The Kiwis proved restarts were possible. And there is one more Kiwi story that cannot be skipped, partly because it is funny, and partly because it nearly caused an international incident. Beyond the operational tests, engineers needed to answer a worst-case question. What happens if everything goes wrong? What if the launch vehicle carrying a nuclear engine explodes on the pad? What if the reactor falls into the ocean? What if the reactor power spikes to maximum instantaneously? For the last scenario, they prepared a special experiment. They took a Kiwi reactor, put it on a flat car, hauled it to a separate stand up on a hill away from the main complex, and in one instant rotated all control drums to maximum reactivity. All at once. Instant supercriticality. The reactor, naturally, blew apart. The explosion was equivalent to about 300 pounds of black powder. Not catastrophic, but impressive. Radioactive debris scattered across the desert. The scientists named this experiment Kiwi-TNT. Kiwi-TNT. A nuclear experiment. Named after the abbreviation for trinitrotoluene, an explosive. In an era when the Partial Nuclear Test Ban Treaty was in force, banning atmospheric nuclear detonations. The Soviet Union detected the radioactive traces through routine atmospheric monitoring. Questions followed.
From the perspective of air samples, this looked suspiciously like a nuclear weapons test. The Americans explained, "No, it is not a bomb, it is a rocket engine. We just blew up our nuclear rocket engine. On purpose, for science." The State Department gave Los Alamos a severe dressing down over the choice of name. "Why?" the diplomats asked. "Would you name a nuclear experiment TNT? What were you thinking?"
Apparently, the project had passed through a multi-level bureaucratic approval process, and at no point along the way did it occur to anyone that naming a nuclear test Kiwi TNT during the Cold War might not be the brightest idea. Here is also where it is worth stepping back and putting this program in its broader context. Project Rover and the Kiwi tests were part of a much larger wave, an era when nuclear energy seemed like the answer to everything. The late 50s and early 60s, atoms for peace, nuclear power plants, nuclear ships, nuclear submarines. In a neighboring zone of the Nevada test site, another project was underway. Project Pluto, a nuclear ramjet engine for a cruise missile. SLAM, the supersonic low-altitude missile, was supposed to fly at treetop level at Mach 3, trailing a plume of radioactive air and dropping nuclear warheads along its route. A weapon so repulsive that even the military eventually decided not to build it.
People sometimes confuse NERVA with these Cold War fever dreams. They hear nuclear rocket engine and think of Pluto, of nuclear aeroplanes, of mad schemes that came to nothing, and they conclude nuclear propulsion was just another Cold War fantasy that did not work. But NERVA was not Pluto. Pluto was genuinely insane. Nuclear aeroplanes were a dead end. Those programs deserved to be shut down. NERVA was different. It worked. It solved a real engineering problem, raising specific impulse for interplanetary missions. It moved methodically from concept through prototypes to a functioning engine. And it was killed not because of technical failure, but because the mission it was built for disappeared. The Kiwis did their job. They proved 4 things. 1. A nuclear thermal rocket engine works. You can heat hydrogen with a reactor and produce thrust. 2. Problems are solvable. Vibrations were beaten. Restarts are possible. 3. Hydrogen is difficult but manageable with proper engineering. 4. If you name a nuclear experiment TNT, diplomats will be unhappy. Concept confirmed. Time to move forward, to build a real engine, one capable of flying in space. And that job was already assigned to another program, running in parallel with Rover, bearing a name that would become one of the most bittersweet symbols of unrealized potential in the history of spaceflight. NERVA, Nuclear Engine for Rocket Vehicle Application. There is something else worth discussing about the safety record at Jackass Flats, because it says a great deal about the culture of the program. The most powerful reactor tested under the Rover program was Phoebus, named after Phoebus Apollo, the sun god. Phoebus 2A, tested in 1968, reached 4,000 megawatts, the most powerful nuclear reactor ever operated on Earth. For perspective, a modern commercial power reactor generates around 1,000 megawatts of thermal output. Phoebus ran at 4 times that and weighed a fraction as much, because it did not need the heavy safety systems, multi-barrier containment, and yard-thick concrete walls of a power station. It sat on an open flat car in the desert, built for one purpose: maximum power, maximum temperature. All the energy directed into a hydrogen stream through a nozzle. Phoebus was not a full rocket engine. It was a demonstrator. Proof that reactors at that power level could run stably. And it ran. 4,000 megawatts with no accident. If you are ever in Las Vegas and have a free afternoon, visit the National Atomic Testing Museum. The Phoebus reactor is there, on display. You can walk right up to it. By size, it would fit in the bed of a pickup truck, which, according to some accounts, is roughly how it was transported on the last leg of its journey. Across the full 17-year lifespan of rover and NERVA, 3 people died in work-related incidents. None of the deaths was caused by the nuclear reactor or by hydrogen. 1 person was killed in a car accident on site. 1 suffocated after entering a nitrogen-purged tank for welding work, a classic confined space accident where nitrogen had displaced all the oxygen and the worker lost consciousness in seconds. The 3rd, the most absurd, died after dousing classified computer tapes with gasoline and lighting them to destroy them. Fire. For a program that operated open nuclear reactors, handled white-hot hydrogen, worked with cryogenic liquids, and remotely drove trains carrying radioactive cargo across the desert, 0 fatalities from the core technological risks is a remarkable record. It speaks to a safety culture that, beneath the jokes and the jackass and Western humor, was serious and effective. Of course, there is an elephant in the room: radioactive contamination. Every Kiwi and subsequent reactor test released radioactive hydrogen into the atmosphere. Debris from the vibrational breakups of Kiwi B1b and B4 is still lying in the Nevada sand. Kiwi TNT scattered radioactive fragments across the desert. All of this was deemed acceptable by the standards of the era. The site was on a nuclear test range already contaminated by hundreds of atmospheric bomb tests. Adding a little more radioactivity to a place where they had been detonating atomic weapons seemed to the engineers negligible. Today, that would be unthinkable. Modern environmental standards do not permit venting radioactive hydrogen into the open air. Testing next-generation nuclear rocket engines will require closed-loop systems where the hydrogen, after passing through the reactor, is captured, cleaned, and disposed of properly. This enormously complicates and raises the cost of testing infrastructure. It is one reason why the Draco program plans to conduct its first test directly in space. In vacuum, there is no atmosphere to contaminate, and the exhaust disperses into infinite emptiness. But that also means the first firing of a new nuclear thermal engine will be exactly that, the first. Without the series of ground tests that NERVA went through, without 20 iterations of Kiwi, each providing data and lessons, the new generation of engineers will rely on 50-year-old documents, computer simulations, and their own courage. It is a challenge, but one that many in the industry believe is overdue. Here is one more fact worth sitting with. In the space industry, there is an informal rule. Technology that has not flown does not exist. You can write 1,000 papers, run 100 simulations, test on the ground until the cows come home, but until it has been in space, it remains ground-based. NERVA went nearly the whole distance, from concept through prototypes, through dozens of tests, through qualification in a vacuum chamber. One step remained, an orbital test. That step was never taken. Draco, if everything goes according to plan, will take exactly that step. For the first time in 50 years, a nuclear thermal rocket engine will reach orbit. For the first time, not on a test stand in the desert, but in space. For the first time, not on a remote-controlled train, but on a rocket. And when, or if, that happens,
it will not be the beginning of a new path. It will be a continuation of what the people at Jackass Flats started in the late 50s. A continuation of Bussard's work, of the Los Alamos engineers, of the Westinghouse and Aerojet designers.
A continuation of the work of people who rode a little train across the desert with a nuclear reactor on a flat car, took apart irradiated hardware with mechanical arms, and one day, probably after a particularly successful test, painted the words Jackass and Western Railway on the side of a locomotive. 50 years is a long pause, but knowledge has no expiration date. The physics written on those yellowed pages from '65 works exactly the same today. Tsiolkovsky's equation has not changed. Hydrogen still weighs 2 grams per mole, and nuclear fission still releases millions of times more energy than chemical combustion. All that remains is to build the engine, put it on a rocket, and fly. But let us stay with this moment a little longer, the moment when it becomes clear the engine works, and ask, how exactly did the engineers get from the shaking, crumbling Kiwi B to the stable, reliable NRX? Because in that transition lies maybe the most important engineering story of the entire program. And it is all about how the core of a nuclear rocket engine is built at the micro level. NERVA's fuel elements were not simply rods of uranium with holes drilled through them. They were sophisticated composite structures, and their evolution from Kiwi A to NRX is an entire chronicle of materials science under extreme conditions. The early Kiwi A elements were relatively straightforward, plates of uranium-235 in a graphite matrix. Graphite is one of the few materials that retains its strength above 4,000 degrees Fahrenheit and simultaneously serves as a good neutron moderator. The moderator is needed to slow down neutrons. Fission neutrons come out fast, around 12,000 miles per second. Slow, so-called thermal neutrons are far more effective at splitting uranium-235 nuclei. Graphite slows them by elastic collisions, like one billiard ball bouncing off another of similar mass. Since carbon atoms are close to neutrons in weight, each collision transfers a significant fraction of kinetic energy. But graphite at high temperatures reacts with hydrogen, forming methane, CH4. The hydrogen literally eats the graphite, carrying away carbon atoms from the structure. Erosion, mass loss, structural weakening. Exactly the problems that showed up in the Kiwi B tests. The solution was coatings. Every fuel element in NRX was coated with a thin layer of niobium carbide, NBC, an extremely refractory compound with a melting point above 6,300 degrees Fahrenheit. It forms a dense, hydrogen-proof barrier on the graphite surface. Hydrogen cannot reach the carbon because niobium carbide stands in the way. But a coating is a thin layer, on the order of a few thousandths of an inch. Between the coating and the graphite substrate lies an interface, a boundary where two different materials meet. When heated to thousands of degrees, these materials expand at different rates. They have different coefficients of thermal expansion. Graphite expands very little. Niobium carbide expands more. Stress builds at the interface. If the stress is too great, the coating cracks. A crack is a door for hydrogen. Hydrogen penetrates, attacks the graphite underneath, and runaway erosion begins. The solution, one of NERVA's key achievements, was intermediate layers. Between the graphite and the niobium carbide, engineers deposited a thin layer of a material with an intermediate expansion coefficient, such as molybdenum. Molybdenum acted as a buffer, smoothing the mismatch. Additionally, the fuel channels were made slightly tapered rather than perfectly cylindrical, allowing the coating to slide along the surface during expansion instead of cracking.
Each of these innovations came from analyzing destroyed reactors. They tore down Kiwi B1b and saw where the coating cracked. They tore down Kiwi B4 and saw where hydrogen had penetrated beneath the coating and eaten the graphite. Every destroyed reactor was a textbook. Every crack was a clue. Engineers read the language of failure the way a geologist reads rock strata. Here was stress. Here was corrosion. Here was thermal shock. By the time NRX was built, all this information had been processed into a design that worked. Coatings held. Channels did not break. Hydrogen flowed through the reactor, heated to over 4,500 degrees Fahrenheit, and exited through the nozzle with almost no core material carried along. These insights about coatings, about intermediate layers, about thermal stresses, about how carbides behave under neutron bombardment, are stored in those yellowed reports from the 60s. Modern engineers working on Draco and other programs find solutions in those reports that they would otherwise have to rediscover through long and expensive experiments. Or might never discover at all, because running those experiments today requires infrastructure that no longer exists. In that sense, NERVA is not just a program that was shut down. It is a library, written with blood, time, and money. A library that cannot be rewritten because the conditions under which it was created, open-air nuclear tests in the desert, unrestricted release of radioactive hydrogen into the atmosphere, 20-plus reactors, each fired, broken, and disassembled. Those conditions are no longer reproducible. Today, you cannot work that way, and thank God for that. Environmental regulations exist for a reason. But the data collected then, under those conditions, is priceless. And it is open, and it is waiting. One more beautiful detail, the geometry of NRX fuel elements. If you have ever seen a cross-section of a NERVA core, and those images are available in declassified reports, it is a mesmerizing sight. The core is made of hexagonal blocks, each about the size of a pack of cigarettes, packed tightly together like cells in a honeycomb. Through each block run 19 channels, thin, circular holes through which hydrogen flows. The outer shell of each block is niobium carbide. Inside is graphite matrix with uranium-235 dispersed through it. The full NRX core contained about 1,600 of these blocks, assembled into a cylinder surrounded by a beryllium reflector. The reflector bounces neutrons escaping from the core back in, so they are not lost, but continue to sustain the chain reaction. Set into the reflector are 12 control drums, each half beryllium, reflector, and half boron, absorber. Rotating the drums controls power. The entire assembly, core, reflector, drums, housing, fits into a cylinder roughly 3 feet across and 5 feet long. The compactness is astonishing when you remember that this is a reactor producing 1,000 megawatts. A power plant reactor of the same output fills a building the size of an apartment block. Here, you could wrap your arms around the housing. If it were not for the radiation, the compactness comes from the fact that a rocket reactor does not need the massive safety systems, multi-loop heat exchangers, concrete containment buildings, and other infrastructure of a ground station. It is designed to run for minutes or hours, not decades. It does not produce electricity. It produces thrust.
and its sole job is to be as hot as possible at the lowest possible weight. The NERVA program was created in 1961, 8 years before the first moon landing, at the peak of American space ambition. Kennedy had just given his speech before Congress. Send a man to the moon and return him safely before the end of the decade. The country burned with space fever. NASA's budget climbed steeply. And in that context, nuclear rocket propulsion was seen not as a distant dream, but as the next step, what comes after the moon. NASA did not simply take over Project Rover and continue as before. The agency built a full organizational structure. And here, honestly, begins the most surprising part of the story. Surprising not for explosions, not for disasters, not for human drama, but for how well everything worked. Rover, the Los Alamos reactors and Nevada tests, became the research branch. Its job? Develop and test new core designs, experiment with materials and operating regimes. NERVA became the engineering branch. Turn those experimental reactors into actual flight-ready rocket engines. To manage the program, NASA and the Atomic Energy Commission, the AEC, created a joint office, SNPO, Space Nuclear Propulsion Office. Dual reporting. One agency owned the rocket side, the other the nuclear side. On paper, this looks like a recipe for bureaucratic paralysis. 2 bosses, 2 sets of priorities, 2 budgets, 2 opinions on everything. And yet, the system worked. Milton Klein, the first head of SNPO, reported to both NASA and the AEC simultaneously and managed to keep the balance. 3 field offices coordinated different fronts. Cleveland handled theoretical work and contractor coordination. Albuquerque managed the relationship with Los Alamos. Nevada ran the test site. Conflicts between agencies happened, but they did not paralyze the work. Perhaps because NERVA was not tied to the moon race, was not under the crushing pressure of national prestige, and people could afford to just do their jobs. Instead of spending energy on turf wars, contractors split responsibilities logically. Westinghouse designed and built the reactor itself. Core, fuel elements, reactivity control, everything nuclear. Aerojet designed everything else. The rocket nozzle, the turbopump assembly, the hydrogen feed systems, the interfaces. Everything that turns a bare reactor into a complete rocket engine. One builds the furnace, the other builds the rocket around it. The reactor design they eventually settled on was designated NRX, Nuclear Reactor Experimental. It was essentially a heavily reworked version of the Kiwi B4, the one that used to shake itself apart, but with fixed vibrations, strengthened structure, and improved channel hydraulics. In September 1964, NRX went to the test stand for the first time. Familiar procedure: train, flat car, stand, hookup, ignition. Results of the first run: power 1096 megawatts, specific impulse 811 seconds. The requirements called for power of at least 1000 megawatts and specific impulse of 825 seconds, with thrust of at least 75,000 pounds. On power, they exceeded the target. On specific impulse, they fell short by 14 seconds, 14 out of 825, less than 2%. In the world of rocket engines, where every parameter is the result of dozens of trade-offs between temperature, pressure, flow rate, and material strength, 14 seconds off on the very first test is not a failure. It is a working result you can refine. An engineer who gets data like that does not panic. He nods and writes a plan for the next iteration. A month later, NRX was restarted, specifically to confirm reusability. Reactor shut down, allowed to cool, fired up again. Everything ran nominally. No vibrations, no damage. Nozzle intact, core intact, turbopump intact.
I want to pause here and say something about why this part of the story is so unusual. We are used to space program stories where everything goes sideways, where rockets blow up on the pad, where fatal design flaws emerge, where budgets triple, schedules slip by years, and blame gets assigned by congressional committees. We are used to it because it happens often. It happened with the shuttle. It happened with SLS. It happened with the Soviet N-1. Space is a brutal arena for ambition. A story about a program that stayed on track, hit its targets, and kept within budget is, strangely, rarer and more valuable than a story about a disaster. NERVA was on track, and the next step, NRX-EST, the engine system test, was designed as a trial by ordeal. Let us torture this engine until it breaks, or until it proves it has no intention of breaking. The test plan was brutal. Multiple restarts at different power levels, shut down at one power setting, restart at a higher one.
Thermal cycling to see how fast the reactor could heat up and cool down. Pushing past design limits to find where the real margins lay. Complete shutdown of external power to make the engine run on its own, from its own turbo generator. And finally, an endurance test, running the engine 10 times longer than it had ever operated before. In February 1966, NRX went to the stand. It ran for nearly 2 hours, half an hour at full power, shut down, restarted like clockwork, operated in every temperature and power regime it was given. Demonstrated autonomous operation without external power, passed everything. One last question remained, and it sounded almost silly but was dead serious. Every test so far had been conducted with the engine pointing nozzle up. In space, the nozzle could point in any direction, up, down, sideways. In zero gravity, there is no up. In theory, this should not matter. Hydrogen is fed by a turbopump under pressure. Gravity plays no role.
In practice, who knows? Maybe with the engine inverted, gas bubbles would collect differently. Hydrogen distribution across the channels would change. Something might go wrong. Theory says one thing, but the engine had never actually run upside down. For the next phase, Aerojet took the NRX design and built a full-fledged engine around it. The XE, experimental engine. Not an experimental reactor with a nozzle bolted on, but a genuine engine with all flight-type systems. Turbopump assembly, control system, onboard power, the full package. And they tested it in conditions as close to spaceflight as they could manage. The engine was placed inside a vacuum chamber simulating space, turned nozzle down, and subjected to the same merciless cycle. Restarts, temperature shocks, endurance, off-nominal conditions, power loss. XE ran for nearly 2 hours and performed 28 restarts. 28. Every one under its own power, in vacuum. For any rocket engine, chemical or nuclear, 28 restarts in a single test session would be impressive, even today. For an experimental nuclear prototype in 1969, it was extraordinary. Let us take stock of what we have at this point. Late 60s, early 70s. NASA possesses a nuclear thermal rocket engine that meets design requirements for power and specific impulse. Restarts multiple times reliably, runs autonomously without external power, and has passed testing in a vacuum chamber in near-flight configuration. The next logical step is to put it on a launch vehicle and send it to orbit. And by every technical measure, it was ready. NERVA was conceived as part of a larger architecture, not an isolated project, but a link in a chain. Apollo leads to a lunar base, leads to a nuclear interplanetary tug,
leads to Mars. The engine was ready. The plans were drawn. The engineers were waiting for the green light. And then, on January 20th, 1969, Richard Nixon moved into the White House. And here it is worth talking about one more aspect of the problem, one that ties together all the threads of our story, about engineering culture and the attitude toward failure. Thornburg, who has traveled the path from the Air Force through NASA and SpaceX to his own company, says something that explains a great deal about NERVA's history and why the program achieved what it did. He says, "Failure is not the opposite of success. Failure is a tool. We break things on purpose to see where a design gives way, what we do not yet know, and what needs fixing. An engineer who is afraid to fail designs everything with enormous safety margins, which means heavier than necessary, more expensive than necessary, and slower than necessary." Old-school NASA, the NASA of Apollo and the Shuttle, operated on the principle of failure is not an option. It sounds heroic, but in practice it means endless verification, endless testing, endless redundancy. Every component checked and rechecked until not a shadow of doubt remains. This costs enormous amounts of money and time. SLS, the Space Launch System, has been in development since 2011, has already cost tens of billions, and runs several $1 billion per launch, because failure is not an option. SpaceX works differently. Break, watch, fix, repeat. The blooper reel of failed Falcon 9 first-stage landings is not a disgrace. It is a training manual. Every failed landing is data. Data you cannot get any other way. Only when you have pushed a design to its breaking point do you know exactly where the boundary lies. And then you can design a system that operates right at that boundary, not with a huge safety margin, but with the minimum necessary one. Lighter, cheaper, faster. NERVA, surprisingly, worked closer to the second model.
The Kiwis broke, and every breakage yielded information. Kiwi B1B shook itself to pieces. Engineers disassembled the wreckage, found the cause, fixed it. Kiwi B4, the same story. 2 years of rework and the problem was solved. Kiwi TNT. They deliberately blew up a reactor to learn what happens in the worst case. Each failure was a stepping stone to a working engine. And the result? NRX went to the test stand and hit its design targets on the first run. Because by that point, all the major unknowns had been eliminated by previous iterations. The Kiwis broke, so NRX would not have to. They paid the price of the unknown. They delivered the data. And when it was time for the real engine, it worked. There is another note worth adding about how NERVA was organized, because the management model matters as much as the technology. The dual reporting structure of SNPO, answering to both NASA and the AEC, created an unexpected benefit. Every decision required agreement from both sides, and that actually sped things up. Because once a decision was made, it could not be overturned by a single phone call from one agency. You needed consensus from both. And consensus, once reached, is sturdier than a unilateral order. It does not get reversed when a deputy director changes. Direct communication channels mattered too. At SNPO, engineers from Los Alamos could talk directly to engineers at Westinghouse and Aerojet. No intermediate approval layers, no memos in triplicate. If an Aerojet engineer found a turbopump issue that required a core redesign, he called Westinghouse and they worked it out together. Then both went to management with a solution, not a problem. And there was trust. Westinghouse and Aerojet had significant autonomy on technical decisions. SNPO set the requirements: power, specific impulse, thrust, endurance, but did not dictate how to achieve them.
This let the contractors experiment, stumble, and find solutions without months of approval for every step. The result was a program that moved from prototype to prototype without multi-year delays. From Kiwi A in 59 to NRX in 64, 5 years. From NRX to XE in 69, 5 more. 10 years from the first flicker on the test stand to qualification testing in a vacuum chamber. By space industry standards, that is blazing speed. For comparison, SLS began development in 2011, first flight 2022. 11 years for a first launch, and that was for a rocket based on proven shuttle technology. NERVA created a fundamentally new technology from scratch, with no precedent in comparable time. Maybe the secret was the people. NERVA engineers were mostly young, graduates of the 50s and early 60s, raised in the atmosphere of post-war technological optimism. They believed that technical problems have technical solutions, that if physics does not forbid it, it can be built, and they built it. Maybe the secret was the context, the moon race, space enthusiasm, the feeling that the future was just around the corner. In moments like that, people work differently. Not for money or career, but for the sense of being part of something larger. Or maybe, and most likely, the secret was the combination. The right people, the right structure, the right moment. Whatever it was, NERVA remains one of the rare examples of a large government technical program that stayed on schedule, stayed on budget, and met its stated performance targets. Which makes its fate, being shut down not for failure but for lack of interest, all the more bitter. Richard Nixon became president, replacing Lyndon Johnson. For the space program, it was a watershed. Johnson had already cut NASA's budget. Money was bleeding into Vietnam. But Johnson did not touch the programs themselves. He reduced funding, tightened scope, but did not cancel projects. Under Nixon, the approach changed fundamentally. Austerity became not a tool, but a goal. And NASA was the primary target. Expensive, visible, politically vulnerable. Events cascaded. Production of the Saturn V was halted. Apollo 20 was cancelled to free up a rocket for the Skylab space station. Then Apollo 18 and 19 were cut. The lunar program, having just reached its peak with the Armstrong and Aldrin landing in July 69, began to collapse before it had exhausted its scientific potential. NERVA held on for a while. And the reason was not technical arguments, not NASA's advocacy, not strategic logic. The reason was 2 senators, Democrat Clinton Anderson of New Mexico and Republican Margaret Chase Smith of Maine, became, in effect, the program's political patrons. Anderson was one of the most consistent and influential supporters of the space program in Congress. He had been close to Kennedy and could play the memory card. This is what John would have wanted. Smith was famous for her independence. She was the one who had publicly stood against Senator McCarthy's witch hunts in the 50s. Both were experienced, powerful, and knew how Washington worked. In December 1970, the Office of Management and Budget recommended killing both NERVA and Skylab. Nixon hesitated. Both programs employed 20,000 workers in California, and he had a re-election campaign in 72. Instead of NERVA, he decided to sacrifice Apollo 17, postponing the final moon mission until after the election. In 71, Nixon tried again, and Anderson and Smith struck back, hard and calculated. Nixon had a pet project, the Boeing 2707, America's supersonic passenger jet, a competitor to the Anglo-French Concorde. Nixon had personally shepherded the program through committees and hearings for years. Anderson and Smith organized a Senate vote and killed the Boeing 2707. Completely, permanently. The project was dead. As a warning, touch our program and we know where yours is. For a time, it worked. Nixon backed off from direct attempts to close NERVA. He switched to a different tactic: slow strangulation through the budget. In '71, Congress appropriated $69 million for the program. Nixon released only $29 million, less than half. The following year, the Senate, with Anderson pushing hard, tried to allocate $100 million and attached legal language requiring the money go directly to NERVA. No diversion allowed. Anderson fought for every dollar. Meanwhile, the program scrambled for new missions. With Apollo winding down, NERVA's original purpose, interplanetary missions using Apollo hardware, was evaporating. NERVA was designed as part of a system. Without Apollo, without a lunar base, without Mars plans, the engine was a solution looking for a problem. A motor without a vehicle. On January 5, 1973, Nixon ordered NASA to shut down NERVA. No Senate vote, no public debate, a directive, and that was that. Program closed. Thousands of people at Los Alamos, Westinghouse, Aerojet, NASA, the AEC lost their jobs. SNPO was dissolved by June. For the engineers, it was a sudden, paralyzing blow. Literally months before the shutdown, they had received a contract to develop a smaller, next-generation reactor. They had work. They had goals. And one day, nothing. 17 years, more than 20 reactors tested, roughly $10 billion in today's money. A working, fully qualified engine prototype. That prototype now stands in a museum at the Marshall Space Flight Center in Huntsville, Alabama. The Phoebus reactor, which reached 4,000 megawatts, the most powerful nuclear reactor ever operated, sits at the National Atomic Testing Museum in Las Vegas. The rails of the Jackass and Western Railway are slowly being buried by desert sand. The program did not fail. It simply was not given the chance to succeed. The engine worked. It was killed not by physics, not by engineering, not by hydrogen's tantrums, but by a president who needed money for a different war, and a world that had lost interest in the far frontier. But something remained that no presidential order can erase. The documents. Thousands of pages of reports, blueprints, test results. Declassified, digitized, available in open archives. And the knowledge. How to build a nuclear rocket engine. How to handle hydrogen. How to survive vibrations. How to operate a reactor by remote control from 2 miles across the desert. That knowledge sat in the archives for 50 years. And the question we come to now is not, why was it forgotten, but why is it coming back? To answer that, we need to return to the people who will fly to Mars, and what 9 months in deep space will do to them. Let us come back to where we started, to Tsiolkovsky's equation, to a rocket flying to Mars, and to the humans inside it. When we say 9 months in transit, it sounds like an abstract number, a line in a table, a technical characteristic of the route. But behind that number lie concrete, measurable, physical consequences for every person on board. Start with radiation. Beyond Earth's magnetic field, the magnetosphere that deflects most charged particles, the crew faces continuous exposure from 2 sources. First, the solar wind and solar flares. Streams of protons and heavier ions emitted by the sun. These can be partly blocked by material shielding. They are relatively easy to stop. Second, galactic cosmic rays, GCR. High-energy nuclei of heavy elements, iron, nickel, silicon, accelerated to near-light speeds by distant supernovae and the cores of black holes. These particles carry tremendous energy. They punch through a ship's walls like a bullet through paper. Worse, when they collide with the heavy nuclei of shielding material, they produce cascades of secondary particles, neutrons, protons, pions, that can be more dangerous than the original radiation. Thick lead armor does not help. It can actually make things worse, generating more secondary particles than it stops. Lighter materials, polyethylene, water, work better, but you need enormous quantities for any meaningful dose reduction. Every month in interplanetary space is accumulated dose. Elevated cancer risk. Animal studies using heavy ion irradiation, simulating GCR, show cognitive impairment, degraded memory, reduced learning ability, behavioral changes. The crew of a Mars ship, arriving at their destination, may not be quite the same people who departed. A brain bombarded by cosmic rays for 9 months straight does not function quite the same way. How different? We do not know precisely, because no human has ever spent 9 months outside the magnetosphere. 4.5 months instead of 9 means half the accumulated dose, half the risk, half the time that cosmic rays are hammering the crew's brains and bodies. Next, the musculoskeletal system. In weightlessness, bones lose calcium at a rate of about 1 to 2% per month. This is measured across hundreds of astronauts who have served long stints on the ISS. Over 6 months, bone density in load-bearing areas, the hips, the spine, drops by roughly 10%.
Muscles atrophy despite daily 2-hour workouts on special resistance machines. Vision deteriorates. Elevated intracranial pressure in weightlessness deforms the eyeball, a condition called SANS, Spaceflight-Associated Neuroocular Syndrome, documented in dozens of astronauts after long missions. 9 months in weightlessness, and you arrive at Mars with weakened bones, weakened muscles, potentially altered vision. And then you step out onto a planet with 38% of Earth's gravity. That is not zero. You will be walking, lifting, working on weakened bones. A broken hip on Mars is a situation for which you have no hospital and no possibility of evacuation. The nearest emergency room is 100 million miles away, and a distress signal takes 20 minutes one way. 4.5 months instead of 9 means half the bone loss, half the muscle atrophy. The crew arrives at Mars in significantly better physical shape. Psychology. 9 months in a confined space the size of a small apartment, with a group of 4 to 6 people. No way out. No fresh air. No sunlight. The windows show nothing but the blackness of space. No real-time contact with Earth. Signal delay ranges from 4 minutes at closest approach to 24 minutes at the far end. You send a message, the reply comes back 8 to 48 minutes later. Real-time conversation is impossible. You depend entirely on the people next to you, and you are entirely locked in with them. Every long-duration isolation experiment, Russia's Mars 500 and others, shows the same pattern. Psychological pressure builds non-linearly. The first weeks are adaptation, even excitement. The first months, routine, settling in. And then irritability, conflicts, sleep disruption, declining motivation, sometimes depression. The longer it goes, the worse it gets. Every additional month costs more than the last. Cutting the transit in half is not an abstract scheduling improvement. It is a concrete reduction in every risk. Radiological, physiological, psychological. Less food consumed, less water recycled, less oxygen generated,
Fewer potential failures in the life support system. Less of everything that can go wrong during 9 months in a tin can between two planets. And there is one more aspect that is often overlooked when people discuss engines for Mars missions: orbit capture. When a ship approaches Mars, it is moving at tremendous speed. To enter orbit around Mars, rather than fly past and disappear back into interplanetary space, the ship must brake. It must perform a capture burn, a retro thrust that slows it enough for Martian gravity to grab hold. The window for this maneuver is a few hours, maybe less. During that time, the engine has to produce enough impulse to shed the excess velocity. Ion engines, for all their spectacular efficiency, cannot do this.
An ion engine's specific impulse can reach 3, 5, 10,000 seconds, many times higher than a nuclear thermal engine. But the thrust is minuscule. The Dawn spacecraft, equipped with an N-star ion engine, changed its velocity by about 60 miles per hour over 4 days. 4 days for what your car does in a couple of seconds. The reason is mass flow rate. An ion engine expels individual ions, one by one, accelerated to enormous speeds. Each ion is fast, but there are so few of them. Thrust equals mass flow rate times velocity. And at a tiny mass flow rate, even with enormous velocity, thrust remains microscopic. Orbit capture at Mars requires thrust. Real, substantial thrust that can change the velocity of a multi-100,000-pound ship by miles per second within hours. Ion engines are physically incapable of this. A nuclear thermal engine can do it. Its thrust is roughly 1/10 of a chemical engine of the same class, but 1,000 times more than an ion engine, and its specific impulse is twice as good as chemical. It sits in exactly the sweet spot that an interplanetary mission needs. Enough thrust to accelerate and brake within reasonable time frames, and enough efficiency to avoid turning the entire spacecraft into one giant fuel tank. One more design point worth mentioning. What does a Mars ship with a nuclear engine actually look like? The reactor emits radiation, neutrons, gamma rays, lethal to the crew. How do you shield people? Heavy lead or tungsten plates around the reactor? You could, but that is mass. Tens of thousands of pounds that, by Tsiolkovsky's equation, demand tens of thousands of additional pounds of fuel. The solution that NERVA engineers found is elegant in its simplicity. Distance. Radiation intensity drops with the square of distance from the source. Double the distance, intensity drops to 1/4. Triple it to 1/9. If the reactor is 600 feet from the crew module, the dose at the module drops to acceptable levels without any heavy shielding at all. A Mars ship with a nuclear engine looks like this. Reactor and nozzle at one end, crew habitat at the other. Between them, a long, lightweight lattice truss, hundreds of feet of it. No lead wall, just distance and light aluminum structure. By mass, almost nothing. By shielding effectiveness, sufficient. The design resembles a nuclear submarine. Reactor in the stern, crew in the bow, compartments and distance between them. Except instead of steel bulkheads, you have the vacuum of space and aluminum trusses. Every one of these aspects, radiation, bones, psychology, braking, shielding, is a different facet of the same question. Can we send humans to Mars and bring them back alive, healthy, and able to work? Chemical rockets say, maybe, if everything goes perfectly, if the crew can endure 9 months. Nuclear thermal engines say 4 to 5 months, twice the supplies, margin for maneuvering, confident orbit capture. Tsiolkovsky's equation still rules, but at 850 seconds of specific impulse,
Its grip loosens just enough for a Mars mission to cross the line from adventure to engineering project. Which raises the obvious question: if all of this is so clear, if the technology was proven 50 years ago, if the documents are sitting in open archives, why are we still flying on chemical rockets? And here it is worth staying a moment longer on how Nixon actually killed the program, because the mechanics of the process deserve attention. Not because they are unique, but precisely because they are typical, and understanding them matters for anyone who wants to know how technology programs die. Nixon did not walk into the Oval Office on day one and sign an order to shut down NERVA. That is not how it is done. Directly cancelling a program that has congressional support is a political scandal that costs votes. Instead, Nixon followed the textbook of bureaucratic strangulation, a technique that has been used dozens of times on dozens of programs since. Step 1. Cut the budget, but not to zero. The program formally survives, work continues, but there is only enough money for the bare minimum. Research slows. Contractors trim staff. Young engineers leave. They sense the program losing momentum and look for work in more promising places. Not everyone goes. The committed ones stay. The ones who believe funding will come back. But the team gradually ages and thins. Step 2. Strip the program of its mission. When Apollo was cancelled, NERVA lost its strategic justification. An engine for Mars ships? Mars mission cancelled. An upper stage for a heavy launcher? Saturn V production shut down. A nuclear tug? For what? There is no space traffic at that scale. Every time NERVA supporters went to Congress for money, they were asked one question: what mission do you need this engine for? And the answer, for future missions that will become possible once the engine is ready, sounded unconvincing. Step 3. Offer an alternative. The shuttle became that alternative. It was sold as a universal space truck that would replace all existing rockets. Why build a nuclear upper stage when the shuttle would fly every 2 weeks and haul everything you need? The argument was false. The shuttle never achieved its promised flight rate and was never cheap. But in the early 70s, no one knew that yet, and the shuttle's promises looked plausible. Step 4. Deliver the final blow once the program is weakened enough that no one is left to defend it. By January 73, Anderson was ill. He would die in 75. Smith had lost her re-election in 72, for the first time in 33 years. The two main defenders of NERVA were off the stage, and Nixon struck, quickly, without discussion. This pattern, cut, strip, substitute, kill, has repeated many times since. George W. Bush's Constellation program started, trimmed by Obama, cancelled. The JIMO nuclear electric probe to Jupiter's moons, funded, then defunded. Every time, the same pattern. Not a rejection of the technology, but a loss of political will. And every time, thousands of people lose their jobs, knowledge scatters, and a decade later, someone starts over from scratch. NERVA is perhaps the sharpest example, because in its case, the technology was closest to completion. One step remained before an orbital test. One launch, one flight. And after that, NERVA would have crossed from ground technology into flight technology. And flight technologies are much harder to kill than ground-based ones. The precedent, once set, works for you. We already flew this. We know it works. Why not fly it again? That step was never taken. And in that, maybe, lies the deepest lesson of this entire story. Not that nuclear engines are possible, that is proven. Not that hydrogen is difficult, that is known.
but that between works on a test stand and works in space lies a political gap that can be wider than any engineering chasm. Draco is the first attempt in 50 years to close that gap. And, characteristically, it is funded not by NASA but by DARPA, the Defense Advanced Research Projects Agency. Because in the 21st century, the argument for Mars turned out to be less persuasive than the argument for defense. Cislunar space, the region between Earth and the Moon, is becoming strategically critical territory. Satellites that underpin everything – navigation, communications, banking, military intelligence – hang in orbit, vulnerable and nearly immobile. Rapid maneuvering between orbits is a military need, and nuclear propulsion is the most efficient way to provide that maneuverability. The irony: a technology built for a trip to Mars may get its second chance, thanks to the needs of defense. The same irony that started the story. Project Rover was born as a military program for ballistic missiles, then became a space project. Perhaps the cycle will close. The military funds the development, and space reaps the benefits. Perhaps. Tsiolkovsky's equation does not distinguish between military and civilian missions. It just counts mass, velocity, and fuel. And the answer is always the same. The higher the specific impulse, the more you can do, for any purpose. And since we are talking about people, let us walk through the specific, physically tangible effects that the difference in specific impulse has on the architecture of a Mars mission. Because 4 months instead of 9 is the tip of the iceberg. Beneath it are dozens of less obvious, but no less important consequences. Start with launch windows. On a chemical rocket using a Hohmann transfer, the launch window opens once every 26 months, when Earth and Mars are in the right relative position. Miss it by a few days, and you wait over 2 years. For a one-off mission, that is annoying but survivable. For a regular supply program to a Mars base, it is a disaster. Every 26 months, one window. If something goes wrong, a delayed launch, a booster failure, bad weather, the next chance is 2 years out. The base needs supplies for at least 2.5 years of autonomy, and every extra pound of supplies is extra pounds of fuel by Tsiolkovsky. A nuclear thermal engine with its doubled specific impulse provides a delta V margin that allows travel on trajectories other than the minimum energy Hohmann transfer. You can fly higher energy but faster routes, so-called Type 2 trajectories that sweep more than 180 degrees around the ellipse, or conjunction-class direct transfers. These routes burn more fuel, but at 850 seconds of specific impulse, the additional fuel costs far less in terms of starting mass. The launch window expands from a few days to a few weeks, and in some cases, to several months. This is a revolution for logistics. Instead of one shot every 26 months, you get a flexible schedule with multiple opportunities per year. Next, abort capability. One of the most terrifying features of a Mars mission on chemical rockets. Past a certain point, there is no going back. You departed, accelerated, settled onto a Mars-bound trajectory, and you do not have enough fuel to turn around and come home. You are committed to a ballistic arc, like a stone thrown across a canyon. If something serious happens on board, a fire, a hull breach, a life support failure, you cannot abort the mission. Apollo 13 could come home because the Moon is close, 3 days away. Mars is 9 months out.
At that distance, turn around and go home is physically impossible on chemical fuel. A nuclear thermal engine does not fully solve this. The physics of distance does not change, but it extends the zone within which an abort is feasible.
With doubled specific impulse, the ship can carry an emergency Delta-V reserve, extra fuel set aside specifically for mission abort. On a chemical rocket, that reserve costs too dearly. Every pound of emergency fuel eats into the primary fuel budget. On nuclear, the reserve becomes affordable. Then there is life support mass. For a 9-month transit, every system has to run without failure and without external servicing for 270 days. Every critical component, pumps, filters, electronics, must be rated for that duration. Plus redundancy. Every critical component is doubled, sometimes tripled. 3 independent air scrubbing systems, 3 water recycling loops, 3 oxygen generators, because a single point failure 8 months from Earth could mean the death of the crew. At 4 months, the reliability requirements drop by half. Components rated for 120 days instead of 270 can be lighter, simpler, cheaper. Some backup systems can be simplified or even eliminated because over a shorter transit, the probability of a simultaneous failure of 2 redundant systems drops significantly. This is cascading mass savings. Lighter life support means lighter ship, means less fuel, means even lighter ship. And finally, communication delay. The signal lag between Earth and Mars varies from 4 to 24 minutes one way, depending on the planet's relative position. But the delay between Earth and a ship in transit is something else. A ship on a Hohmann trajectory gradually moves farther from Earth. At the start, the lag is seconds. After a month, minutes. After 3, 10 minutes. By midway, 10 to 15, 9 months of steadily growing isolation. On a 4-month transit, the maximum delay at midpoint is smaller because the ship is traveling faster and spends less time at large distances. This does not eliminate isolation, but it softens it. The crew stays within near real-time range for a larger fraction of the trip. Knowing you will hear back in a minute is a fundamentally different psychological experience from knowing the answer will arrive in half an hour. Every one of these factors, launch windows, abort capability, life support, communication, is a separate facet of the same crystal. And every one of them turns in the crew's favor when specific impulse goes from 450 to 850. A nuclear thermal engine does not solve every problem of a Mars mission, but it weakens each problem just enough for the mission to cross the line from barely possible to hard but doable. And in engineering, the distance between those two categories is the distance between a fantasy and a funded project. Here is maybe the simplest way to frame everything in our story. In public discourse, nuclear space propulsion is often discussed in terms of pro and con. Supporters say, doubled specific impulse, faster transit, less radiation for the crew. Opponents say, a nuclear reactor in space is dangerous, politically unacceptable, expensive. Both sides are right, each about their own part of the argument, but they are arguing about different things. The question is not whether nuclear propulsion is needed. The question is, for what mission? If the goal is to land a 1-ton rover on Mars for science, a chemical rocket will do. We have done it. Perseverance flew just fine on a chemical Atlas V. For robots, transit time does not matter. If the goal is to deliver 10,000 tons of equipment to Mars for a base, without crew, chemical rockets will handle that too. You just need more launches. At the projected cost of a Starship flight, tens of millions per launch, you can fly dozens of cargo runs. Expensive but feasible. Robots will wait 9 months.
Nuclear propulsion becomes not just useful but essential when you add humans to the equation. Living, breathing, irradiated, bone-losing, homesick humans. For them, 9 months is not a statistic, it is a biological limit. And a nuclear thermal engine is not an option, but a condition under which a Mars mission crosses from heroic gamble with high risk of death to difficult but manageable engineering challenge. Apollo was a heroic gamble, and it got lucky. 13 times they sent people to the moon. 13 times they brought everyone home alive, though Apollo 13 showed how thin the margin was. A Mars mission cannot afford that level of risk. Too far, too long, too many failure points. A different approach is needed. Not heroic, but engineered.
With safety margins, redundant systems, abort options, short transit times. Nuclear thermal propulsion is not a magic wand. It does not solve everything. But it solves the one key problem, the mass budget. And in doing so, it frees the hands to solve all the rest. Because when you have twice the payload at the same starting mass, you can afford more shielding, more supplies, more backup systems, more of everything that turns a gamble into a project. Here, maybe, is the simplest way to sum up our entire story. Tsiolkovsky's equation says, to fly far, you need a lot of fuel. Chemistry says, fuel can only be so efficient. Physics says, but there is another energy source. Nuclear, millions of times more powerful. Engineering says, we already know how to build this. We did it 50 years ago. Politics says, we shut it down. History says, the knowledge survived. The future says, maybe it is time to try again. Between these voices lies our story, the story of one number in one equation. Exhaust velocity. A number that determines whether we can reach another planet, not as robots, but as people, and come back. The answer, as almost always in these stories, is not about physics. The physics has not changed. Tsiolkovsky's equation is still there. Hydrogen is still the lightest element. Nuclear fission still releases energy millions of times greater than chemical combustion. Everything the NERVA engineers knew remains true. What changed was the context. After NERVA was cancelled, the shuttle era began, a program designed as a workhorse for routine low Earth orbit flights, 200 to 250 miles up. For those tasks, chemical engines are more than adequate. The question of Mars dropped off the agenda for decades, replaced by more mundane goals: satellite servicing, space station assembly, microgravity experiments. When the Mars conversation returned in the 2000s, the world looked different. Private space companies, SpaceX, Blue Origin, sharply reduced the cost of getting to orbit. Falcon 9 offered launches for $60 million instead of $1 billion per shuttle flight. Starship promised even less, and people began to wonder whether maybe chemical rockets would be good enough if you just made them big enough and cheap enough. Brute force instead of elegance. And yes, within limits, it works. For cargo missions, for unmanned probes, for delivering equipment to Mars, chemical rockets are fine. A robot does not care if the trip takes 9 months, but for humans, the equation is different. A cheap launch does not make the transit shorter. It does not reduce the radiation dose. It does not turn 9 months into 4. It lets you send more mass, but over the same 9 months. And so nuclear propulsion came back. Quietly,
without fanfare, through research programs and modest budgets. The US Congress approved funding for nuclear space propulsion research, $125 million. A DARPA program called DRACO, Demonstration Rocket for Agile Cislunar Operations, aims to demonstrate a nuclear thermal engine in space by the mid to late 2020s. For the first time in half a century, there is a real prospect of a nuclear rocket engine in orbit. NASA considers nuclear propulsion a key element of future Mars missions. The agency's estimates say a crewed transport ship would need 400 to 2,000 kilowatts of power. Solar panels can provide that near Earth, but at Mars distance, sunlight intensity drops to 43% of Earth levels. At Jupiter, 3.5%. A nuclear reactor works the same, regardless of distance from the Sun. Intermediate solutions have also appeared. Jeff Thornburg, an engineer with 30 years of experience across the Air Force, NASA, Aerojet, and SpaceX, where he was one of the architects of the Raptor engine for Starship, founded a company called Portal Space Systems. It is developing a solar thermal engine, same principle as nuclear thermal. A working fluid is heated by an external energy source and expelled through a nozzle. But instead of a reactor, the heat comes from concentrated sunlight. A large parabolic mirror focuses the sun's rays onto a small area, and the working fluid, ammonia, methane, eventually hydrogen, passes through that focal point, heats up, and produces thrust. Less efficient than a nuclear engine, but more efficient than chemical. And critically, no regulatory or political problems associated with putting a nuclear reactor in space. Thornburg is direct about his long-term vision. My dream is nuclear thermal propulsion. But you cannot buy a nuclear reactor at the hardware store. Solar thermal is a stepping stone. A way to develop the critical technologies, high-temperature heat exchangers, nozzles rated for over 2,000 degrees, working fluid management, while the nuclear industry matures for space applications. When the day comes, the mirror gets swapped for a reactor. Same principle, different heat source. This modularity is one of the underappreciated advantages of the thermal approach. A chemical engine is married to its fuel. Energy and mass come bundled together. A thermal engine, any thermal engine, solar or nuclear, is free. You can change the heat source without redesigning the rest. Mirror, reactor, even a laser beam from an orbital station. Those are all different ways to heat a gas. The gas, the nozzle, the turbo pump stay the same. And then there is the most intriguing idea of all, a hybrid nuclear engine. Remember, a nuclear thermal engine gives you high thrust and moderate specific impulse, 800 to 900 seconds. An ion engine gives you tiny thrust and spectacular specific impulse, thousands of seconds. Each excels at different tasks. Thermal for powerful maneuvers, departure, braking, orbit capture. Ion for long, patient cruising acceleration. A hybrid engine uses the same reactor core in two modes. Mode 1, thermal. Control drums rotated to the reflective side. Reactor at full power. Hydrogen flowing through the core and out the nozzle. High thrust, fast maneuver. Mode 2, electric. Drums rotate to the absorbing side. Power drops. The reactor switches to generating electricity through a thermoelectric generator or turbine, and the electricity feeds ion engines. Low thrust, but extraordinary specific impulse, and the ship slowly, steadily gains speed over weeks and months. For a Mars mission, the hybrid would work like this. Powerful thermal boost on departure from Earth.
rapid initial velocity gain. Switch to electric cruise mode, slow but efficient acceleration throughout the transit. On approach to Mars, switch back to thermal for the braking burn and orbit capture. No hybrid nuclear engine has been built or tested yet, but all its components exist separately. Nuclear reactors, thermal nozzles, generators, ion engines, control drums. Physics does not forbid combining them. Engineering is a matter of time, money, and will. There is also a more conservative variant. Simply put a multi-megawatt nuclear reactor on the ship and use it to power standard ion engines. No thermal mode, no hydrogen, just electricity and xenon. The perennial problem with ion propulsion has always been power. Solar panels produce too little electricity at large distances from the sun. A nuclear reactor removes that constraint. With enough power, ion engines can deliver reasonable transit times. Not as short as a thermal NTR, but much better than solar electric alone.
The catch is that such a ship would need massive radiator panels to dump waste heat, since the only way to shed heat in space is infrared radiation from large surfaces. A nuclear electric ship would look like a long truss with enormous radiator wings, reactor at one end, habitat at the other. None of these variants, thermal, electric, or hybrid, is science fiction. All are grounded in physics that has been understood, measured, and verified experimentally. The gap between understood and built is money, time, political will, and engineering labor. But there are no physical prohibitions. Tsiolkovsky's equation does not forbid nuclear propulsion. It forbids chemical rockets from getting to Mars efficiently. A nuclear engine is the legal, physically sound way to loosen his equation's grip. There is a thought I want to return to at the end. It is not about rockets or equations or hydrogen. It is about how technological progress actually works.
The NERVA program lasted 17 years, cost $10 billion in today's money, and was shut down without a single flight. You could look at that and say the effort was wasted. Here is what actually happens today. Every time a modern engineer sits down to design a next-generation nuclear engine, they start by opening the archives. They find a PDF, a scanned, yellowed document from 1965, prepared by Westinghouse or Los Alamos National Laboratory. In that document are test results that cannot be reproduced today. Cannot, because the test site no longer exists. Because today, no one would be allowed to vent radioactive hydrogen into the atmosphere. Because half the techniques were classified, then declassified, then forgotten. Because the people who remembered the details retired and passed away. That PDF is the only source, and the data inside it is valid. The physics has not expired. The results are reproducible. The engineering solutions are applicable. Jeff Thornburg describes it with the precision of someone who has done it personally. NASA and the Air Force have been fantastic at developing cutting-edge technology. And then they take the results and put them in a crate next to the Ark of the Covenant in the warehouse at the end of Raiders of the Lost Ark. I have been lucky. A few times in my career, I walked into that warehouse and pulled something out. This is not a metaphor. The full-flow staged combustion engine was first developed and tested in an Air Force lab, where Thornburg worked as a young engineer in the late 90s. The program ended. The results went on a shelf. 15 years later, those results became the foundation for the Raptor engine, the one now flying on Starship. A seed planted by a government program bloomed in a private company a decade and a half later. NERVA left the same kind of seeds.
data on hydrogen behavior at extreme temperatures and neutron fluxes, fuel element designs capable of surviving 4,500 degrees, testing methodologies for nuclear rocket engines, reactivity control solutions for compact reactors, radiation protection protocols, remote disassembly procedures for irradiated hardware, those mechanical arms in Nevada. The NERVA prototype stands in a museum in Huntsville. Not a model, not a mock-up, but a real engine that actually ran. Phoebus, the 4,000 megawatt reactor, the most powerful ever operated, is in Las Vegas. The documents are in open archives. The rails of the Jackass and Western Railway are being slowly buried by desert sand. In the space industry, there is a term, heritage. It means a technology that was developed, tested, and documented by predecessors. NERVA's heritage is one of the richest and least utilized in the history of spaceflight. 17 years of work, billions of dollars, more than 20 reactors, all recorded, all preserved. Waiting.
And here is perhaps the most important lesson of this entire story. Not that politicians kill good programs. We know that. It happens constantly. But that knowledge, once created, does not vanish. It settles into the foundation. Someday, someone will build on it what its creators did not get the chance to build. And perhaps the deepest lesson has nothing to do with rockets at all. It is about what happens when a society stops investing in fundamental research. Thornburg speaks about this with the frustration of someone who has watched it happen for 30 years. We are robbing our own R&D. When I started my career 30 years ago, it was bad. Now it is worse. Private capital and venture funds chase returns and stock prices. They have no incentive to fund technologies that do not yet have a business model. And it is exactly those technologies, the ones with no business case today, that turn out to be the engines of progress tomorrow.
He gives a specific example from his own career. The full-flow staged combustion cycle he worked on in the Air Force lab. The military funded it because it was a frontier technology. Nobody knew for sure if it would work. There was no business case, no return on investment within any planning horizon. Government money took the first step, and 15 years later, that technology was at the heart of an engine flying on Starship. A private company, SpaceX, picked up government heritage and turned it into a commercial product. NERVA is the same pattern, only on the scale of decades. The government invested $10 billion, got a working engine, cancelled the program. The knowledge went on a shelf. And now, half a century later, when the question of Mars is back on the table, that knowledge is in demand again. What if NERVA had not been cancelled? What if Nixon had not slashed the budget? It is hard to build alternate histories, too many variables. But here is a fact. In 1971, NASA had a working nuclear engine and a Mars mission plan. If funding had continued, even at reduced levels, by the 80s, there could have been an orbital test. By the 90s, a first interplanetary flight with nuclear propulsion, possibly unmanned, possibly to Mars. Instead, 50 years of pause. 50 years during which the only way to travel beyond Earth orbit remained the same as it was in Tsiolkovsky's day: chemical combustion and Newton's third law. The same 450 seconds of specific impulse, the same glass ceiling. Sometimes the most expensive thing is the time lost to inaction. We have come a long way from Tsiolkovsky's equation, which locks us inside an exponential trap, through the design of an engine that cheats that trap, through the tantrums of hydrogen, which makes the cheat possible and simultaneously unbearable, through the story of the people who built that engine in the Nevada desert,
hauled it on a little train and watched it work. Through the politics that killed it, and through the slow, cautious return of the idea in our own time. The entire story is about one variable in one equation: exhaust velocity. A number that determines how much fuel a rocket needs, how long the trip takes, how much cargo you can carry, and ultimately, whether humans can reach another planet as a biological species, not just as robots. Chemical rockets give us 450 seconds of specific impulse. That is enough if you stay close to home. Nuclear thermal engines give 850. That is enough to fly to Mars and come back. In the world of exponentials, the difference between those two numbers is not quantitative, it is qualitative. It is the difference between 9 months in a tin can and 4. Between, will we have enough food and let us take a spare generator? Between a desperate gamble and an engineering project with safety margins. We know how to do this. We knew it 50 years ago. The engine standing in a museum in Huntsville is not a model, not a concept, not a dream. It is a prototype that ran, that was tested, that passed every requirement thrown at it. It was killed not by physics but by politics. And if we ever seriously decide to go to Mars, we will have to go back to what was already done. Pull the documents from the archive, train a new generation of engineers, rebuild the test infrastructure. And maybe, just maybe, send a little train down the tracks through the desert one more time.